Integration of inverse trig functions. So we've so far covered integration using substitution. Okay, with indefinite integrals, so we make this substitution which will be given to you, you change it, manipulate it so it becomes an easier thing to integrate, and then you've got to change your answer back into what the variables are. You also had looked at integration with definite integrals, so the only thing different you need to do is change the endpoint integration with respect to the new substitution. However, you don't have to change variable back because you are going to get a constant number.
Email.
Might slow it down a bit then. Okay, so the last thing we did yesterday, we looked at how to integrate sine squared and cos squared of ax. Okay, so we've made the substitution using cos 2x is equal to cos theta minus cos squared x minus sine squared of x, and we manipulated it so that we can integrate what we've learned in mathematics. So the last thing we need to do is integration of inverse trig. So there is a section in your HC course, it focuses on inverse function, okay? So we'll look at that towards the end of the course. So in short, an inverse function is found by interchanging the x and y values of the function. So for example, we have the function y equal to 2x, take away 5, we swap the x and y values over. So the y becomes x becomes y, and they're rearranged for y the subject. Okay, graphically, what this is a reflection about the line y equals x. So here's our original function, y equals 2x take away 5. There's the dotted line, y equals x. So if you fold that over the dotted line, okay, and left the print, you're going to get that line there. Okay, so that's the idea of an inverse function. So, looking specifically at the sine, cos and tan inverse function. So, the inverse function of y equals sine of x is y equals sine inverse of x. So if we swap the variables, so x is sine of y. Okay, and we solve for y, so y is going to be sine inverse of x when we find the angle there. Right, so we've got the sine curve there. Okay, we've got the line y equals x, and if we fold it over, okay, we're going to get the graph of sine inverse x as that section there. Now, we have to restrict the domain, because when you have the inverse function, you want to restrict the domain, okay, because otherwise it's just going to keep going like that, and then going to fail the vertical line test. So that's why we have to restrict the domain. Morning. Alright, so same with cos of x, so we take the inverse function of that, so here's our normal cos curve. There, we restrict the domain, okay, so from here to here, here. Okay, to restrict that domain, we fold it over the reflection on the line y equals x, and then we're going to have the cos inverse function like that. Okay, so this is going to be 1 and this is -1 on here. So we fold it over and we have the inverse function for cos. Okay, so the inverse function is just a reflection on the line y equals x. Now tan, slightly different again, because if we take the section here of tan, we reflect it on the line y equals x, and it's still going to be a function. Okay, so we'll continue going. We're going to satisfy the vertical line test just for that section between the asymptote, and we fold it over, and we're going to get our tan inverse of x going that way. So that's the summary of inverse functions. You will look at there is a topic of it in later extension 1, and you'll look at that towards the end of the course from memory. Okay, so is there any questions about the understanding of inverse functions? Alright, here's your rules. Okay, these are all in your notes. Actually, I wouldn't write these ones down, I would write the next page, because these are just the generic one for when you have ones. Okay, we will look at a general proof. Okay, so when you differentiate sine inverse of x, you're going to get 1 over the square root of 1 take away x squared. differentiate cos inverse of x, you're going to get negative 1 over the square root of 1 take away x squared. And you differentiate tan inverse of x, you're going to get 1 over 1 plus x squared. Alright, so if you integrate each of these respective three things here, you're going to get back to your original function. Okay, so that's the definition of integration. When you integrate this one, okay, because this and this, the only difference is the negative sign. Okay, so when you integrate this, you get cos, but you can also write this as negative sign. Okay, because it's a minus of that, isn't it? So I can do that. Alright, so from memory, this and this are on your formula sheet. I don't remember who that one is. Alright, so that was going to be the way to help you remember that. Sorry. And that will be on your reference sheet from memory. And here's probably specifically what's going to be there. So imagine this will be there, and that will be there. Okay, here are your general definition. Okay, so when you have sine inverse of x over some constant a, okay, now we've got the a's inside part of the differential. Alright, so a's, a and a. Instead of 1s for those variables, because we're dividing by 1, we can just simply substitute 1 in there. So that's the result. So when you integrate each of these three things here, you're going to get back your sine, cos and tan, etc., etc. Right, so let's have a look at some proofs. So 1, 2, and 3. Right, so number 1. So let's say y is sine inverse of x over a. Okay, so by definition, moving that back over the other side, it becomes sine of y is equal to x over a. X equals a sine of y. Right, dx, differentiate x with respect to y. Okay, so that a constant stays there. So when you differentiate sine, you get what? Cos of y. And we need dy dx because we are differentiating that. Alright, so dy dx is going to be 1 over a cos y. So far. Right, so that's equation 1. Okay, so sine squared of y plus cos squared of y is what? Yep, remember this is 1. You're not going to forget this ever again, aren't you? Right, so cos squared of y is going to be 1 take away sine squared of y. And sine of y is x over a, so sine squared of y is going to be x on a squared. 2. Take away x on a, or squared. So I'm going to have put it all over common denominator. The a squared take away x squared on a squared. Okay, and then take the square root. A squared minus x squared on a. Right, so we're going to neglect the negative square root. Okay, because we're just substituting, showing a proof. Okay, so that's number 4. I'm going to put that into number 1. So dy over dx. dy dx is going to be 1 over a, and then substitute cos y. And that's the proof. Alright, so going backwards, so if you integrate that, you're going to get back to your original function, which is cos inverse of y up the top. Alright. Now the proof is pretty much exactly the same for number 2, and number 3 is pretty much the same again. Okay, so instead of this step here, because you're going to be differentiating tan to get sec squared, so you're going to use your identity with tan squared and sec squared in here, substitute it all in, and you'll get that expression at the end. Okay, so you need to remember these integrations there and there, alright, so that you can do the integration. Right, so I'm going to just stop it there. Right, so let's do some examples. So the integral of dx over 4 take away x squared. Okay, so this is really a squared take away x squared. Right, so what is, doesn't match with one of the rules that we had on the previous page. Yep. So dx on, 1 over a squared take away x squared. Okay, it's going to be sine inverse of x over a plus your constant integration. Alright, so what's the value for a? 2. Okay, this is going to be sine inverse of x over 2 plus c. Right, second one. So negative 1 over 9 take away x squared. So again, it's a squared take away x squared dx. So the negative is cos. Okay, so 2 options you can write. So cos inverse of x over 3 plus your constant integration, or what else can you write?
Negative sign.
Negative sign. Alright, so if you differentiate both of those, alright, well, with the proof I've just done, you will get that same answer. Alright, so writing either of those will be fine. So from memory, your formula sheet won't have the cos, your reference sheet, you have to double check this, I don't remember. Okay, but you incorporate the negative sign in that, and that will help you to remember that from memory. Any question? Alright. This one doesn't have the square root. Okay, so the format is a squared and a. Alright, do they match? Okay, so we've got a squared and a do match. Alright, so without the square root and the plus on the denominator is a tan inverse. Okay, so the tan inverse x over a, x over 2, plus your constant integration. Alright, starting to be different. What do you notice different about this one compared to what we've done so far? So, yep, okay, so what you need to do is you have to have x, the coefficient of x as 1. Alright, so you're going to have to factorise. So, it's going to be integral of dx all over the square root of 9. So you need to take out that constant and factorise. So you're left with 1 over 9, take away x squared. That you're going to get coefficient of x is 1, get squared, so is 1. So take the square root of 9, which is 3, so it's going to become a third integral of dx over the square root of 1 over 9 take away h squared. Right, so 1 over a squared, the square root of h squared take away h squared. Okay, so we can integrate that. So what's the rule? What's the formula? Okay, sine. Okay, so third out the front. Sine inverse of x over a. So a is what? 1/3. You've got to take the square root. So x over a third plus c. And of course you can tidy that up. So third sine inverse of 3x plus c. Right, so that's the sort of manipulation you need to do so that you can continue to integrate. Right, e, so I've got the square root, okay, so I'm looking at my either my sine or cos inverse when I integrate. I've got a 2 on top, I really need a 1, okay, so I'm going to start manipulating it. I'm going to take the 2 out the very front of the integrand. So then I'm left with dx over, and remember this constant needs to be 1 out in the front of x squared. So you have to factorise. So take the 25 out. So you have 4 on 25 take away x squared. Okay, so this is that times that, so we can take the square root of 25 and move it out the front. So 2/5. Okay, and the rest of it is 4 over 25 take away h squared. So that is your sine. Okay, sine inverse of x, or whatever the variable is, could be y, this could be theta, whatever, okay, but not always x, over the value of a. Okay, so x over, so this is a squared as part of the formula, so that would be 2 over 5 for a. Plus your constant integration because it's an indefinite integral. Okay, so if you can do this in one step, just flip that fraction over. Okay, that's fine. So 2/5 sine inverse of 5x over 2 plus c. Okay, any questions? Go ahead following this. So of course we can have definite integrals. Okay, and you can be asked to do the area and volume, etc., etc. Alright, just like any other integration question. So dx over 1 plus x squared is 10. Okay, so one without the square root and the plus sign. Okay, nice simple one to finish. The 10 inverse of x over a. So a is 1, so a squared is 1, so a is 1. From root 3 and 1. Okay, so when you integrate, you need to have these in radians, okay? You can't just write them in degrees. Because the degree is an angle measure, but radian is specifically a length of an arc. Okay, so you'll be looking at the area if this was an area question. Right, 10 of what angle makes root 3? 60, which is what in radians? And 10 of what angle makes 1? 45, which is what in radian? 5/3 take away pi on 4. Which is simplified to what? So? Pi on 12, yeah. So it'd be 4 pi, take away 3 pi on 12, which is pi on 12. Right.